Well, we will start this seminar with the presentation of Dr. Montserrat Garcia with the title Polymer Inorganic Nanocomposites, Influence of Colloidal Silica. Welcome, Montserrat, and please go ahead with the presentation.
Thank you very much, Dr. Olmos, for the presentation. Indeed, I'm going to talk to you about the influence of nanosilica in ceramic matrices and also in polymer matrix. I have to say thank you to this nanolab, Mesa Plus, which is located at the University of Twente, because all the measurements, most of them were done there. And of course, I have to acknowledge a lot of people that were part of this research. University of Eindhoven, University of Delft, Groningen, and several groups of the faculty of Twente, of the university, and also some discussions with people from the industry like DSM. I'll talk about myself. I'll give you some introductions and goals, and you can also follow the presentation here at the bottom of the slides. Who am I? Well, I did chemistry at UNAM in Mexico. I did polymers at the Material Institute. I did phytochemistry. I work with plants. I also work with ceramics. And I did my PhD at the University of Twente. I became a polymer scientist at the National Dutch Graduate School. I also did some postdoc at another company in Leiden. I have some patent contributions of result of this work. I have worked in several companies, European Patent Office, Rijswijk and Tyco in Breda, and in Pentair. And nowadays, I'm a chemical advisor at Emerson Valves and Controls, doing water certification, and I enjoyed some tennis and diving and movies. One of the things that I would like to show are the fact that this research is going on, even though it started with me a bit more than 20 years ago. People are still reading, people are still downloading, people are still citing me, which is very nice. So I will start. This is the presentation about myself. I will go on with the introduction. And of course, we can use different type of reinforcement with different matrices. In the first thing that comes to my mind is to this nice example of nylon 6, with the addition of 5% of less than 5% clay. You can see the improvement in mechanical properties. So, okay, we know then that the addition of filler in the inorganic fillers in ceramic materials and in thermoplastic materials improve the mechanical properties. But let's focus on the tribological properties. The applications that we find with these ceramic materials like aluminum and zirconia are well known. Examples of applications are in ballpoint pens, and bearing and cutting tools. So let's see. We know that if we decrease the friction, we can also have a very good high friction usually results in high wear. So if we improve the friction, if we decrease the friction, we are going to decrease the wear and our material will be more durable. The idea of this is to have a self-application system in which we don't add a third phase, like an oil or something like that, that will decrease the friction of the material. I'm talking about the sliding friction. How do we do it? In a pin on this setup. So one of the goals that we have with these new materials with ceramic and alumina, zirconia with copper oxide, and we tried really different inorganic fillers, is to decrease the friction for below 0.2. The method, as I mentioned, was in a pin on this setup. So you have here the rotating disc, you have the ball that can be alumina or zirconia, some load, and then you can have nice systems to see how the filler influence the friction properties. We did some pictures in which we studied the wear tract. We added 5% of copper oxide to zirconia, and here we saw the best results. This is the characterization, and this is the morphology with the macrostructure. I'm coming back to this in the conclusions, but what I want you I want your attention on this table, because with the zirconia, we decrease the friction 0.4 units, which was quite remarkable at that moment. By means of several methods and characterization, we could show that the copper oxide was working a self-lubrication system for the zirconia. So this resulted in a patent application, because instead of decreasing the friction 0.2 units, we decreased it 0.4. So we were very, very positive about the results. But now the question is, okay, let's go nano. We knew from some previous researches that adding clay as low as 5% will result in a high improvement of mechanical in the mechanical properties like tensile strength of tensile modulus. But what about the friction? So the challenge of this research is to have a very nice dispersion. Here is something that caught my attention, because this was a review on tribomechanical properties of nanoparticle film nylon composites. For this, we didn't use ceramic materials, but we did use thermoplastic materials like nylon, like polypropylene, like high density polyethylene. So it was a very nice research, because you can play with all type of thermoplastics, and also you can play with all type of nanoparticles, but we chose the silica particle. And in this review of March 2021, well, this is my research, was the first one being mentioned, the reference 77. So this is the one I want to talk to you about. Nylon 6, nanosilica 2%. And this review is the first one mentioned. Now, with this part of the project, we have also some collaboration with the rubber group, polymer group, mechanical engineering groups in Princeton, again, Mesa Plus, St. Owen, Delft, and some measurements also in the United Kingdom. Again, you don't have to, you cannot do this type of research alone. You shouldn't, actually. While using nanoparticles, well, you have a different stresses, you have a different grazing and compressions. You can, nanoparticles also are very, very interesting in the world of modeling. We also have a nice theory behind this. I'm coming back to that one as well. But let's say the main goal is the use of nanosilica in a polymer matrix. We have a 20 different particle size, 10 nanometers, 20 nanometers, 30 nanometers. In this case, even though we could make the nanoparticles in our lab, the goal was not to make a nanoparticle, but was to use it in a matrix. So, and the challenge is to have a nice dispersion of the silica. So if you go macro, it's not the same to go nano, because if you go nano, you can also have the silica flocculated, because the silica particles at low pH have the tendency to bond each other for this type of electrical charges. Here you can see this one in this ternary system, in which this is the polymer the acid and the water. What happens here is that we, in the experiment of the project 2, we have the nylon. You can also have different nylons, of course. We dissolve the nylon in formic acid, and then we add the silica particles. All this was done in a clean room that we have. So we let it dry, and then we could check the microstructure, and we got this nice picture in which you can see the nanoparticles. Again, these dots are silica, because also we check it with EDX and other type of characterization methods, but they are not being shown here. But this was one of the first articles that we could publish in which the nanoparticles are nicely dispersed in this nylon matrix. From the mechanical properties point of view, this is without any filler, and with 1, 2, 3, 4, 5%, we have some improvement. But again, our goal was more to look at the tribology. Yeah, this is the disc, and this is the setup, the pin on the setup. You see, you leave the disc here, and then there is also the ball. You start sliding. You have some word tracks. I'm sorry if I go a bit too fast, but I want to show you a lot. And we look at the word tracks, and this is the nice part of the research. Here, you see this is the nylon 6, the polymer, yeah? And with 2%, look at this big jump. So that led to a second patent application. The same happens also with the ceramics. So this was actually a door opening to try different things. Because of this result, I later went to another company called CAM Implants to have a project with implants. Instead of using nylon, we did the nanoparticles in ultra high molecular weight polyethylene that is being used in the legs and in the hips. We also try to look at the membrane properties. Okay, let's see, this is let's make a membrane out of it, and let's see how the properties changed with the pure polymer and with the addition of nanoparticles. We try to look at the permeation properties. Again, this was not the main goal of the research, but you can also have the validation of models. Mori Tanaka model kernels help inside. You can also use different polymers, a Colomba DSM, and you could also have a higher molecular weight of nylon, a lower molecular weight. Of course, you should be careful with the certain point, the nano world is too much. So that's why we just focus on one type of particle, one size, one polymer. And then we can draw these conclusions that the nanofillers have a positive effect on the properties of the matrix in modulus and friction and wear. It changes the permeation properties of the materials. We could also look at the predictions, the modeling. It was a very good one, the Mori Tanaka model, that was good. Okay. The part with the modeling, even though we spend a little bit of time with it, is that the models do not include the chemical effect of the filler matrix, the formation of voids around inclusions, the nano effects of even a combination of all of them. So the topics to be discussed in this research is that what type of nanoparticles you are going to add to which polymer matrix. The influence of the well-dispersed silica nanoparticles, like below 30 nanometers in nylon 6. It can also be nylon 6,6, nylon 11. And the mechanical properties that you can improve. Groups are looking in the nylon, silica, nylon nanosilica, but different ways to do it in situ polymerization and so on. That was at the beginning, but still, we are still doing that research, nylon and silica. We try to improve the modeling. And above all, we want to go big. We want to see if we can actually use those materials. So what happened is that we took that project to a company. Let's see to have it in a large scale. So we went to DSM and working with them, they really liked the project, and we tried to do the configuration of the screw, and I was a couple of days over there. We did the composites. The morphology was not as nice, but it's me some many years ago. And the 10 pictures are shown, one of the 10 pictures is shown here. This is number 6, but as you can see, there is some aggregation. Of course, we did some characterization during all these years with the resonance, XRD, DCS. Anyhow, the main conclusion is that the mechanical properties with nanoparticles changed, friction were changed, crystallinity changed, rheology changed in different way as the bulk material. There are many things to look at. The practical work to zoom in is enormous. You can improve the macrostructure. You can make more dense materials. You can try different metal oxide. You can try different polymers, etc. And here are very few, well, not very few, but from article from my PhD research that we did, for instance, polyamide 6 nanosilica here. And here we have the transport properties, the membrane also resulted in another article. We also have a polymer silica nanocomposite, so polypropylene, sorry. So we changed from nylon to polypropylene. Here we have friction studies. So every chapter became an article, and the patent applications are here. Dense comprising a member of ceramic materials, so the patent international application here, and also a Dutch international application. And well, this work was presented in different countries, and we are very proud of it, especially me. That's my story I wanted to tell.
Thank you very much, Montserrat. And we can start with some questions. Luis, Jaime, if you have any question to Montserrat, please go ahead and be sure Montserrat will try to answer.
Hello? No, go ahead, Luis. Go ahead. I wait.
Yes, thank you. Thank you very much, Montserrat, for this very nice presentation. The audio quality is really good, so I didn't miss any detail this time. Yes, we know that dispersion is very important aspect, when doing nanocomposites. I want to ask you, how do you improve the dispersion of silica nanoparticles, and if you use any quantitative measurement of the dispersion?
You can improve it. There are some research done by changing the surface. So using some agents to change the hydrophilic surface of the silica to have it hydrophobic. So if you have this hydrophobic phase, you will have a nicer bonding with the polymer, because the polymer is also hydrophobic. So you can have a kind of modify the surface. This is how you can improve it. We didn't do it. We wanted to have it simple and see, well, not so simple, of course, but we want to show first without any agent. is how you can improve the dispersion. But that was just another research. It's something to look at. It's very nice and interesting point that you mentioned. So we, how we quantified the dispersion, how much was dispersed? No, we look at the characterization in a qualitative method with the TEM, and we look how the dispersion was in the polymer matrix, but more qualitative. And then we look at the tribological properties. But that's a good point to look at in the future.
Okay. Yeah, thank you. Actually, before I forget, I have another question from from the previous Dr. Monia's question. How do you realize you have copper oxide and you don't have metallic copper, for instance?
Sorry again, how did you?
How do you know that you have copper oxide in the matrix, in the polymer, and you don't have, for instance, metallic copper? Because EDS only measures the presence of an element, but the oxidation stays you cannot see by EDS.
Yeah, indeed. There also is just the element, copper or oxide. Yeah, you don't really, I will say what Feynman said, and you also need a lot of imagination in this world, because we look at the copper and the oxide and the amount that is with the NMR and infrared and so on. So you could see, well, the amount of copper oxide, the copper with oxide, it will match copper oxide. But to be 100% sure, no, it's not like this, indeed.
And I have one last question. Have one question of my own. I see that you process nylon by a dissolution process. You want to scale up by an extrusion process. Will be there any problem in this change from a solution process and to an extrusion process? I'm telling this because I have worked with nylon before, and doing that, working with nylon in an extrusion process is really headache. It's a nightmare. So how do you expect that this scale-up process will be modified and the research will continue in a higher scale?
Actually, what we used was a different silica for the. Indeed, it was not so easy to have the lab scale to a large scale, because the colloidal silica is very expensive. The nanosilica was very expensive. So we use tons of polymers. So we use a silica powder. So then we cannot, in that part of the project, we didn't go one-to-one from small to big. We had to change the silica to powder to have it not so costly. So I don't expect you have to do a lot of trial and errors in the companies to do it. But of course, we only have like some months to try this. After having 3 years of nanocomposites, we have few months to do this. I wanted to try it. We did it, but with different silica. So I expected to have it like it's very difficult. It is achievable, but you need time. You need time, definitely. And to see what it will be the best silica for the polymer you are using and the method and the extrusion method you are using. So that's a different parameters. That's another project.
Yeah, definitely. Okay, thank you very much.
Thank you for your questions. I'm glad that you could follow it.
Yes, I did.
Jaime, some questions for Montserrat.
Yeah, yes, I have some questions. Let me have just 2 questions, okay, and then a third one not related to the research about the permeation. You say that you measure permeation also?
Yeah, we could do the permeation. We didn't go into detail in that. We just we saw that there was a difference. And then that was it.
You
It was kind of like this, if somebody wants to go on with this project, that could be very interesting.
Okay. And with regard to the research, do you have any mathematical modeling on what is going on to say, you know, this is the friction and this is the forces acting on this, because you talk about the rheology of these compounds. Do you include any rheological modeling of the phenomena?
For
Why-
friction and so, no, it's just for the behavior of the particle in the matrix. No, we didn't go that way.
Okay.
Interesting, also for the future, nano world.
Okay, and on the other hand, you show here some DSC, no, the crystallization.
Yeah, it's one of many again, and we could see that the polymer and the switch and the different curved by adding the nanocomposite. This is an example of a polymer of molecular weight 35,400. So you have 2025 and then 2021 in the heating curve number 2.
And the point is here, at what velocity is the cooling and heating occurring in the instrument? I don't know what type of instrument you use, because that of the instrument versus the real work in a company, I mean, when
yeah, that's true. I will look at it. I have the data in the in the book, but and then I can send it to you. The conditions. Yeah,
But,
indeed, it's different.
have you used the Metro Toledo instrument to measure high velocity cooling?
No.
Okay. Yeah, because there is a big difference, no, between what we do in the lab and then in the industry is tenfold, 100 times faster, no, than what we do the measurements at the lab. Yeah.
Indeed, and also the temperature, you see the disaggregation, and it's a lot of things taking place. But okay.
Okay. Now, tell me, this is, I see that this, what you presented are papers from 2001 to 2004, something like that?
Yes. It was when I started this research.
Okay. Can you tell us about your recent research or your recent responsibilities? I would like to know more about what is going on now.
What I do and what I'm doing the chemical advice. I work when I actually got in a company called Tyco. I don't know if you know it. There is Tyco in Monterrey. There are 5 different departments. Tyco, fire security, medical application, engineering application. I was working in engineering application, engineering application because of the project of the friction. I helped to develop a butterfly valve. It's a very technical word. It's a valve, you know, a butterfly valve that opens and closes. And normally the market is dominated by metal valves. Everybody is familiar with metal valves. My job was to bring into the market a composite valve. So then the idea was to make it with nylon, but even though I enjoyed work with nylon, the application was also for the water industry, and nylon will not be my top first for water. So I had to choose. I had the responsibility to choose the materials that will be used in a valve made out of plastic, of composites, to replace the metal valve, but in certain sectors. I cannot say the type of material that I use because it's a patent and it's a secret, but it's also thermoplastic material, and it's also composite material. And I'm very happy to say that we develop the new valve, and now it went into the market. It's already 10 years in the market.
Okay.
And we also I did some research in the rubber, because you have to do sealing in a valve. The valve has to seal. So then we went in that directions to look the rubber, because the rubber has to be certified to be accepted for the drinking water. So what I do is, well, besides to develop the composite valve that was into the market already, it's called Composil, and I sent parts to different labs in France, in UK, in Germany, and in the Netherlands to make the possible the water certification in different countries, and then we can ship this valve to those countries. So I'm responsible not of the shipping, but of the passing of the lab, because, for instance, if you have a material that has isocyanate, then it cannot pass the drinking water application.
Yeah.
So I'm responsible of water certification, and also I give the chemical advice for chemical industries. If I don't need to go to the plants, I only receive a paper with the chemicals involved. For instance, what for do you want? Do you want the valve for tomato juice? Okay, tell me what do you have in the pipeline. Okay, now we want Heineken, the Campina, milk. So the pipeline, the valves are being used in different companies, in the food industry, drinking water, and so on. So I have to check, I have to tell them what type of valve to use, like compost seal, or metal valve, or with a coated, with a epoxy coated. For instance, if the application is for a marine application, in this salty water is different than in the Black Sea, or in Siberia, or if the conditions and the cold weather, or in Australia. If sometimes in Australia they say, well, could you please let us know if the valve stands, how much UV light does it stand? Something that we are not being asked in Russia. So then I had to say, well, for this company, you have to use this valve. And for that company, that valve is what I do also, give advice.
What you do at this moment, okay, is what you're doing at this moment.
Yeah, at this moment, I look at the mechanical, the chemical ingredients that is being in contact with the valve.
Okay, and tell me, how do you envision this shift of coming from the industry to a university? For the position you are being offered, how do you envision this? What is your vision?
I've been teaching in secondary school before coming to the Netherlands. Secondary school, high school, and university in the Faculty of Engineering. When I came to Twente, I also gave some teaching to students from Twente. Nowadays, as I said, I'm part of the project from a school in Colombia, and I also part of the committee of a PhD in Durango. So I was asked to be part of the committee. I have some people working for me at the company and also at the university. So I don't have a problem with teaching or being in front of the group. I enjoy it, and I give lectures, so that's nice.
Okay, and with regard to well, I'm the dean, okay, say dean for consulting, okay, also continuing education and consulting. How do you feel about if you come here, besides teaching, being as a consultant also? I
love it.
Yeah, I expected to.
Well, I like it very much. I feel very lucky to be a chemist and to be in the field I am in nanocomposites. I feel very lucky, and it's not only do research, it's having a link with the companies, and is working in research and development. And that is something always like the CRI that I always have. Okay, what I have, I would like to write an article, and I also would like to go beyond that and have a lot of collaboration. Yeah, I like that.
Okay, okay. And the other thing is, do you still have contact with the Mesa Plus? Do you still have with the ecosystem for entrepreneurship in the university?
I have contacts there. Yeah.
Okay.
Very, very, very good contacts.
Okay.
Even though I went in a different direction, but I work with them. Actually, I do 10 pictures because I have the composite valve, and sometimes we have a valve that is being shipped back. Like what happens with this valve? So why is a failure of the valve, or it's a failure of the customer, of a failure of us? So I said, well, let me see what happens in the valve. So I have sent parts of the valve and parts of the rubber that is being damaged to the nanolab. So I am still in contact with them.
Okay, because no, let me tell you, because we are, as I told you at the beginning, before this recording again, okay, we are having an agreement. Okay, we are about to sign an agreement with them for a double joint degree, okay, in PhD, and also for the undergrads. Okay, so it is important for us the contacts there, so we can keep to make more to make it smoother. Okay, the transition on the students. And also,
I could have. Yeah, sorry.
No, you could what?
No, I could arrange a tour if you want to go, and we can have a tour at nice.
And the other
and talk to nice people there, to nice researchers and professors. Could be nice.
And the other thing will be with the ecosystem, okay? Because what we want to do is to do research with to being conscious on how to use it and how to get a business out of the research that we do, okay? So are you in contact with the entrepreneurial aspect of the university? Because they have a center, no, for entrepreneurship.
I have somebody even better. I have somebody that is working at Shell that is doing that with the universities, and that's a very is the person to talk to.
To whom? Excuse me.
Is somebody that works for Shell and part-time being a professor. It's called Dr. Ariana Meyer.
Okay.
And I can give you the contact. This is really the person you need to talk to for that. It's really good.
Okay.
And I have the contact. I know him.
We have some PhD students that would like to have the experience at 20, okay, but with the mind set that they will do entrepreneurship with the research they get, okay.
Oh yeah, yeah.
Okay.
No, it's really the person to talk to, because he knows where to go, and it's a very good professor.
Okay.
And contact with Shell. Do you know Shell in Mexico?
Yeah.
Okay.
Yeah, and you were mentioning to have contacts in different laboratories around Europe. Okay, do you have also contacts in America besides Mexico?
Besides Mexico, no. And I had it in Princeton, but he moved to Canada to work for electrical engineering. So I don't have it in. Let me think. I know people that could have contacts in USA depending of the project. Okay. Because there are some people that there was a professor, it was my professor that went to I think that Connecticut, but now he came back to the Netherlands, but I could ask. Okay. Well, no, it's just to know how the liaison, the network that you have, okay, how can we have a good use of that network for research and for entrepreneurship? Even though I do have, of course, my friends are chemists, doctors, so they have contact also with other institutes in USA. in that sense, if we have another talk, then I could look where, to whom.
Okay. Okay. Well, thank you very much for your answers, and I would like to have a contact with you so I can exchange some information. I am
Sure.
to travel to Twente sometime this semester. Okay.
Oh, cool.
Okay.
Great. Let me know, then I can join you.
Okay. Thank you. Thank you very much. I'll let you know.
Thank you.
Thank you, Jaime. Thank you, Luis. Montserrat, thank you very much for your presentation, for all your comments, and very useful in the future. So we finished this seminar. We thanks very much to the time to Dr. Jaime Bonilla, Dr. Luis Marcelo Lozano,
Thank you.
and thank you for you, Montserrat. We will be in contact with you as soon as possible for continue with this process. Good morning, everyone. Good afternoon, Montserrat.
Thank you very much.
Thank you, everybody.
It was a pleasure.
Bye-bye.
Bye.